The Bouncy Button project is all about switch bounce and debounce. If you're unfamiliar, DigiKey has an excellent 3-minute video on YouTube. Essentially, a switch's contacts may physically bounce when activated. This bouncing generates multiple signals and can cause a number of problems. The Bouncy Button project takes a humble Arduino and turns it into a powerful button bounce analysis tool. For this one particular task, I actually find the Bouncy Button project more useful than even a fancy oscilloscope, mainly due to the ease of data collection and analysis. The Bouncy Button project really shines here. Alright, let's see it briefly in action. We're going to connect a switch, collect some data, and then analyze that data. It's really easy to use the Bouncy Button project. Open the sketch in the Arduino IDE, click Upload, and while that's happening, grab yourself a switch, connect one side to ground, connect the other side to pin 4, and when it's done uploading, we should be good to go. Don't worry about the low memory available message. It's fine, we're super careful with RAM, intentionally. When you're ready to test, click the serial monitor button in the top right, and you'll see it prints out a little splash screen with some version information, the project URL in case you forget it, and right now it's telling us we need to release the button. The button is currently pressed. Okay, so let's do that. So let's release it. And right away it says, hey, new record, 812 nanoseconds. Pretty good switch. All right, and then it tells us to press. So let's press. We press, new record, 629 microseconds. And basically you just do this as many times as you want. When it says press, you press it. When it says release, release. I like the big text there because it makes it easy to kind of tune out a bit. You know, watch a movie or some YouTube videos, listen to some music. There's a lot you can do from the terminal. If you want to send commands, go to the top, send in the question mark, and it'll print out the possible commands for, you know, adding different sections or deleting a last test if you accidentally glitch. But for now, all we want to do is select all the data in here, and on Windows, you can go Control-A, Control-C, and then we're going to go to the project webpage here, Bouncy Button. You scroll down, there's a link to the analysis tool, and you can use this offline, download it, or online. And we're going to clear the below sample data, paste in our data, and click Parse Below Data. I'm going to hit F11 in Chrome to go full screen to give us a bit more space. Okay, graph and analyze. If all you're interested in is the max bounce, you can get that number right here. So roughly 8.2 milliseconds out of a total of 100 tests. I also like to check out the waterfall. I find it pretty interesting. So if you click on there, it'll center it for you. Each row in this graph shows an individual bounce test. So the majority of the press and release tests lasted less than 1,000 microseconds, except for one. We had one where there was a giant period where it was low for 8.171 milliseconds, and then it popped back up high. My favorite view to look at the waterfall, though, it is kind of interesting to see them in chronological order, but if we go up to the top and we click on Sort by Duration, let's go Graph and Analyze again, click on the waterfall. So right away we can see that the majority of the releases were like near perfect. Like if you look in some of these here, single transitions for the majority of them here. One transition, one transition, one transition. And if we scroll up further though, we get into the press tests. And here we see we've got like 7 transitions, 19, 15. Let's zoom in right here. Look how there's a very consistent pattern to how this button behaves. So initially we start off high voltage, then the button is pressed. It slams down for a short amount of time. So this one here is around 7 microseconds. There's a little blip of a high voltage, and then it goes down low again for about 17. Anyways, look at this. There's kind of a consistent behavior there. There's a line here, bounces low, bounces high, and then there's a big period, roughly around 300-ish microseconds, and then it bounces again, bounces again. Anyway, I find that fascinating. We get some box plots here for max bounce durations, longest pulse duration, transitions per activation, the pulse width of individual like bounces within a test, and then there's full-on table data here, where if you want to, you can actually copy the individual transitions too. Anyway, lots of data here. I hope the demo showed the main value of the project. even in comparison with more expensive scopes. Easy data collection and powerful analysis. I should also mention that there's a companion GitHub repo where I, and hopefully others, upload their button tests and experiments. But what if you are a hobbyist with a lower cost oscilloscope? Well, you may find it difficult to measure button bounce properly. You can either detect short pulses or record long enough to be sure you captured the full bounce. I actually really like my oscilloscope, my picoscope. It's a quality tool and provides great value, but this is an area where it really falls short. As recording length increases along the x-axis, so does the width of pulses that the scope will miss. If my recording length is 100 milliseconds, I can't consistently detect 16 microsecond or shorter pulses with my scope. This problem is common across low-cost scopes, not just picoscope. I should also mention that picoscope does have many more capable models if you're willing to spend significantly more. So how bad is it if our scope misses 16 microsecond pulses? Well, it's pretty bad actually. You can see this anecdotally in the image here. All of those pulses are less than 13 microseconds. We can also check the stats. There's a lot of info here, but the key takeaway is that the large majority of bounce pulses are less than 16 microseconds. Now this data is from an excellent cherry switch, but it is also similar to the bounce data I have for an old really bouncy switch. I'm curious to check more switches in the future. The scope misses pulses because it lowers its sampling rate to record longer. It's not doing anything wrong, it's just a normal trade-off. You need a more expensive scope with lots more memory if you want to capture everything. But this also brings up the question of how long do we actually need to record to test switches properly? To answer that question, let's consult the debounce OG, Mr. Jack Ganssle. If you haven't already seen his article, definitely check it out. It's fantastic. One of the nicer looking buttons he tested bounced over 150 milliseconds. I've actually seen bounces over 500 milliseconds, although that is fairly rare and usually with pretty old buttons. I'd personally recommend recording 500 milliseconds or longer when testing switch bounce. But like we just saw, this is problematic for low-cost scopes with limited memory, but not a problem for the Bouncy Button project because we cheat. With a simple Arduino Uno or Nano, you can detect very short 62 nanosecond pulses and record long enough for even the bounciest of switches. But how is this possible? Well, we cheat and we use some tricks. To detect those high-speed bounces, we rely on the microcontroller's edge counting peripheral. Every rising edge causes timer 0 to increment. We sample the edge count in digital pin every 1.25 microseconds, about 20 CPU instruction cycles. If a change is detected, it is logged with a 16-bit high-resolution timer. And yes, the AVR does have a Schmitt trigger. Schmitt triggers are actually super important when dealing with button bounces to prevent garbage data. Now, is the Bouncy Button project useful for you? Honestly, probably not, unless you are generally interested in electrical phenomena or doing something interesting with buttons. If you don't want to worry about switch bounce, that's fine. Just buy a switch that, is a quality switch with a bounce specification in the datasheet, or debounce with 50 milliseconds, which usually works. Not always, but usually. 50 milliseconds might seem slow, but it still allows 10 presses per second, which is very fast for regular users. There are a few good reasons to be interested in the project though. One of them is that it makes it really easy to check your buttons. Most switches don't specify bounce time on a datasheet, and I've actually seen a few new switches bounce a surprising amount. And let's not forget about those beautiful rustic buttons you salvaged for a fun project. They can sometimes bounce a lot, but can be really worth it. They don't just look good, they have a certain weight, travel, and force that make them feel great, not at all like a flimsy, cheap micro switch. For my own projects, I sometimes run a game with my kids and their friends called Jurassic Spark. I'll skip the details, but a switch plays a central role in the game. I've been using a basic light switch, but I'll be replacing it with a big old chonky button that feels and looks like it came out of the jungle. It's almost like a movie prop. The project is also great for running different experiments. Why do buttons bounce at all on release? Isn't that weird? I get it on press, but on release? Does a switch's bounce behavior change from use and age? Which bounces more, normally open or normally closed switches? Do capacitors actually help? What about wetting current of a switch? And Can a capacitor to ground actually kill a switch? Lots of interesting things to explore. It's also great for performance tuning your debounce algorithm. Here's a real-life example with a surprising result. Both of these buttons are barely used, but one of them has a max bounce time of over 133 milliseconds, and the other button performs nearly perfectly. Neither button specifies a bounce time. Any guesses? Well, here's the performance of the no brand button sold by Banggood. Each row shows either a press test or a release test. The tests are sorted by duration here. We can see that its max bounce is just over 1.2 milliseconds. That's quite good. Let's take a peek at the stats. We can quickly see the max and median results for bounce duration, longest pulse, and also transition count. I often check the press and release max bounce duration too. Most switches that I've tested are pretty asymmetric. In this case, the bouncing for pressing is a lot more than for releasing. Overall, I'd say this is an excellent button. And then there's this switch. We see a fair number of tests that exceed 50 milliseconds. That's not good. Not all of the tests are shown here, however, as I've zoomed in to make it easier to see. Let's check the stats. The median bounce is good, 85 microseconds, but the max bounce is nasty. It's also interesting that presses bounce about 4 times longer than releases. But curiously, the release median performance is 5 times worse. I just double-checked the program using a spreadsheet because I felt like this is weird, but it's correct. The box plot agrees. You can see the line inside each box. Overall, I'd say this button has good, if not great, median performance, but it has too many bad bounces. The Judco switch was probably not designed with bounce in mind. I did some searching online and found that it was used in a lamp product. I just wanted a nice looking panel mounted switch. I have a number of videos planned for the future. I'll probably release them like maybe once a month. Things like how it works internally, do capacitors kill switches, how we can improve old switches like those beautiful old retro switches, answering some curiosity questions, and then some goofy experiments just for fun. Thanks for watching.